All right, we are up and running. So, how is the knapsack problem coming? Did anybody get a start on their maxval function? Not yet. There's time. You can you can code it up and get it to run on small cases without the caching. You can very definitely add the caching at the end, like we did with Fibonacci yesterday, right? You can write the recursive version of it, but it will run slowly, and on even modest size problems it may run too slow to finish. But for small cases, you can totally ignore the caching, ignore the dynamic programming part, and just concentrate on getting the recursive behavior to work correctly. So doing the maxval function itself, and then go back and add the caching of the results. Looking into possible other algorithms, but not on the actual programming assignment. Can you explain why we can't use struct.var equals string var? Instead, we have to use string copy. You mean looking back to like plates? Like the license plate thing? Because strings, okay, so let's do that. Is it possible to change the date to Tuesday? Is there something going on Monday in other classes, like some other due date? Oh, physics midterm on Monday? Sure. Yeah, I can change the due date for PA5 to be Tuesday morning instead of Monday. I'm okay with that. Let me make a note. All right. So yeah, let's play with strings inside GDB and see what exactly happens. All right, so let's play around with some strings here. So I'll have a character array. I'm going to set this to char star buffer. I'll set it equal to hello. I'll see if it's equal to hello, and if it is, we will say all is well. Otherwise, we'll say uh-oh. And if I run this, it tells me all is well. So at first glance, it looks like doing a double equal sign is a perfectly fine thing to do. But it's a bit deceptive. All right, so let's let the person type in something. Okay, so we're going to say hello with an uppercase H. We're going to take off the null terminator at the end. We're going to print out the contents of buffer inside angle brackets so we can see exactly what it looks like. We're going to print out its length, which will help us confirm that it's you know, actually the same string, and then we'll see if it's equal to hello. That's okay. Okay, I'll be nice. Right, so I'll say HELLO, and it confirms, you know, the string is HELLO and its length is equal to 5, but it's not equal to HELLO. So there's something happening here. But what it is exactly clear. So let's compile this with GDB. And let's step into this. So it says hello, it asks us to type in something, we say HELLO. Alright, if I look at buffer, it's the string HELLO. And it confirms that when it prints it out, and it prints out its length, and it's so on. Yeah, it came early this week. Let me do this differently. All right, let me back up a moment. Let's go back to what we had before. All right, so I'm going to make two buffers. They're both pointers to character arrays. One is going to say hello, the other is going to say hello. We'll print out the contents of the first one. We'll say if buffer equals buffer2, all is well. And that's going to work fine. That's going to say all is well. So let me go into my other version. Alright, so I have a character array buffer. I have buffer2 is hello. I'm going to use an fgets to read in buffer. I'm going to take off the null terminator, print it out, and then see if it's equal to buffer2. And here we get into problems, right? Because you You know, the buffer is hello, it's 5 characters, but it's not equal to HELLO. So let's run that in GDB. And we'll say hello. And its length. Okay, so print print buffer. Buffer is this string HELLO. Buffer 2 is also a string HELLO. They point to the same characters, but we're about to execute this statement if buffer equals buffer 2. Right? Buffer is pointing to a location in memory that has the string HELLO. Right? But it's actually stored at this location in memory. Whereas buffer 2 is stored at this location in memory. So you have two different locations in memory. They both contain the same string, the same set of characters followed by a null terminator. But I'm not asking, if I look at the characters at this address up to the null terminator, and I look at the characters at that address up to the null terminator, are all of those characters the same, and does the null terminator occur at the same spot? That's not what this statement says. This says, is this variable equal to that variable? And in fact, they're not. Buffer is equal to 7FFFE340. Buffer 2 is equal to 55554934. They're not equal. Right? But we're not really interested in whether this number and this number are the same. What we're interested in is that the things at that first address and the things at that second address are the same character by character, and the null terminator is at the same point. And the only way we can do that is by examining each of these locations one by one and seeing if the thing at that location is the same. And then seeing when we hit a null terminator in one, have we hit the null terminator in the other. We need to write a function to do that. That's what string compare does. Right? It does exactly that loop. It goes through, it reads what's at each location, compares it, and loops through until one of them hits a null terminator. That's a really long-winded but very detailed answer to that question. All right, cool. All right, other questions? So in case you didn't catch it, I'm going to move the due date for PA5 to Tuesday. So Tuesday morning at 8, because apparently there's a physics midterm Monday. But it's early enough, I'm not going to give bonus points if you turn it in Monday. How do we declare a global variable? If you declare a variable outside of a function, it's global from that point in your file onward. So if I say main, anything that I declare inside here is local to main. And once main exits, it's gone. But if I have another function, right, this cannot access any local variables I declared in here. Any variables I declare in here are local to fun, and when fun exits, those variables are gone. But if I declare a variable here in between functions, this is global from this point on down. So fun could access this variable. Any other functions that I write below this in the file could access this variable. What happens in fun stays in fun, exactly. But main cannot access this variable. If I want main to also have access to this, I should declare this before main, so just in the very top of my file. And I'm going to suggest try to avoid splitting globals across multiple files. You can do it. You can use a keyword called extern to indicate that this is a global variable defined externally. But it's another level of things to figure out. If you want to work with that, that's fine, but be aware that it takes extra stuff to do that. And so if you can stick to, you know, a global defined inside one file, that's going to make life a little easier. So, and you know, we joke about evil globals, but your cache is probably best done as a global array, right? To make it available independent of recursion. I would just make your save array, you know, something declared before your main program, and just give it a name. Don't call it A or I or something, but give it a name that you know, minimizes the chance of stepping on it with a local variable. Can we go over again what happens after the base case gets triggered for PA5? Let's see. The base case for PA5 is when you try to find the maxval of a bag that has a capacity of 0 and just return a 0. But we don't always come down to that base case. So, we're going to do some of these calculations. Right, so if we have n plus 1 items to choose from, take the value of the first item, take its weight away from your capacity, find the maximum value you can get in the rest of the bag, add that to the value of the first item. If we put in item 1, take the weight of that away from the capacity, find the maximum value you can get out of the remaining space in the bag, and add the value of item 1. And do this, you know, for all the items in your list of possible items you can put in your bag. But be aware of two possibilities. One, if the weight is bigger than the capacity, don't do that calculation. So don't call maxval with a negative argument, because it makes no sense. It's saying my bag holds 5 pounds, but you know, if I put in this 5,000 pound car, I get, you know, $100,000 worth of value, plus, you know, there's no space left in the bag, so I get 0. Well, that's not a valid calculation, right? You can only say that this is a possible value I can get if it's possible to put this item into a bag with that capacity. So don't use this in your calculation if that argument is negative. And that's different from simply returning 0 if your capacity is negative. Because if my capacity is negative and I say, well, this is just 0, I'm still adding the value of that item that doesn't fit in my bag. So you got to totally shunt this. You got to totally say, nope, I'm not going to calculate that because item 1 doesn't fit in my bag. So of the items which you can legally fit in your bag, you calculate each of these values and you find the largest and you return that as your maximum value. And the edge case really is when no items fit in your bag, which is what will happen if your capacity is 0, none of your items are going to fit. But also, you know, maybe your capacity is 1, but all of your items weigh more than 1. And so it may be that none of these are considered, right? In which case you just return a 0. So return 0 if your capacity is 0, return 0 if there are no possibilities of items you can put in your bag. That's really your base case. And you may never get down to 0 when you call maxval. If your items weigh 2 pounds and your capacity on your bag is 3, right? I don't think you'll end up calculating maxval of 0. You'll calculate maxval of 1, and that's it. But that's okay, right? As long as you're not endlessly making recursive calls to maxval, right? So let's pull out that example a little bit better. So let's say I have a weight and a value, and this weighs 2 and is worth 10, and this weighs 4 and is worth, 15. And your capacity equals 3. All right, so I'm going to do the following calculations. I'm going to calculate the value of this item 10 plus maxval, so this is to find maxval of 3. I'm going to do the value of item 1 plus maxval of the capacity minus the weight is 1. And I'm not going to be able to consider item 2 because it weighs more than my capacity. So MV3 is going to make a recursive call to MV1. Okay, maxval of 1, my capacity is 1. I can't put in this first item because it weighs too much. I can't put in the second item because it weighs too much. There's nothing I can put in my bag, so the maximum value I can get is just 0. And so there's no recursive call made there. And that kind of gets handled depending on how you do your maxval calculation in this loop, right? So you could make a function that tells you, I wouldn't do a function, I would just do it in a loop. But you could make a function that takes an index, and gives you back the value of this calculation. But largest equals 0. And then iterate from I equals 0 to num items minus 1. If weight I is less than or equal to capacity, possible equals value I plus maxval cap minus weight I. Don't try to copy this down because it's pseudocode. So if I can fit this item in my bag, then calculate the value of that item plus the maxval of the remaining capacity. That's a possible optimizing solution, right? If possible is bigger than largest, largest equals possible, right? So something like that will take care of finding the maximum of these. Don't spend a day on Stack Overflow looking for a function that takes the maximum of an arbitrary number of values. You can do that, but you don't have to, right? You're calculating these one at a time, compare them to your largest value that you found so far. And this automatically takes care of the case where this condition is never satisfied because everything weighs more than what your bag will hold. And when you come out of this loop, your largest will still be equal to 0. And then you need to do something additional in here to keep track of the combination of items that get you this largest value, so that when you exit, largest equals 18, but the combination to get that is to use 2 pens or whatever. Structure of the whole thing, just hold data and weight, no pointers or anything like that. I don't think you need any pointers in here other than, you're using arrays, which are pointers, but I don't think you're doing any pointers. You don't have to do any mallocs or frees or things like that. So the maxval function returns the maximum value out of that's possible for whatever capacity you passed to the maxval function. So if you call maxval 5, you get back, how much you can get out of a bag that holds 5. All right. So a similar problem is the rod cutting problem. And this is another one of these things that lends itself well to dynamic programming. And the setup is the following. You have, let's say, a rod of some kind of material, and you have the ability to cut it in 1-inch increments. And this rod has some length, len. And, you know, sometimes people come by and they want to buy, you know, a 12-inch piece of rebar, right? And they want the whole thing intact. And you can sell that for a certain amount. But sometimes people really want, you know, 4 3-inch pieces because they're working on some project and they need these little tiny pieces of metal. And you can cut this for them and sell them, you know, 4 3-inch pieces. Or somebody may want 1-inch pieces and they're going to weld them together to get whatever length they want. And so if you have a pricing table like this, which says what the value is on the street for rods cut into certain lengths. For example, let's say a 5-inch rod is worth, you know, $10. A 4-inch rod is worth $8. 3-inch rod is worth $5. But 2-inch rods are really valuable, so those are going to be worth $4 each. And a 1-inch is worth $3 because those are really useful. And so your question is, what's the most economically profitable way to cut up this rod and sell the pieces? So we could sell it uncut for $10. We could sell it as a 4-inch and a 1-inch piece for $11. We could sell it as a 3-inch and a 2-inch piece for $9. We could sell it as 5 1-inch pieces for $15. Right? So what's the best way to cut this up and maximize how much we can sell it for? Let's see, question. Is going to be practice for the final? I already posted on Canvas some practice questions for sorting and heaps and things like that we have not had ODPs on and that we're not doing programming assignments for. But, you know, all this other stuff that we're doing programming assignments on and so on, you know, you're getting tons of practice. Yeah, and there's some quizzes. You're getting lots of practice on that. And you know, even though PA4 is done, if you're not quite sure how your code worked, or if you didn't get delete to work or something like that, right? You can go back and you can you know, continue working on those assignments, and you can come by office and we can talk about them and so on. That's all probably your best way to prepare for the exam, is just make sure that you're up to speed on the programming assignments, the ODPs, do the quizzes that are on Canvas, which close sometime this week. Yeah, I think Friday. And definitely do those practice problems that I posted on sorts and heaps, because that's fair game. And we're going to talk about tries probably next week. Oh, did I have a try question on the quiz? I probably did, didn't I? Okay. Well, let's talk about tries tomorrow then. Will be a good breaking point for this stuff. All right, we'll go through tries tomorrow. Good, that gives me another day to prepare for dropping eggs. All right, so we can define a maxval function whose purpose is the following. If I have a rod of this length, what's the most money that I can get by cutting it up and selling the pieces? So if I want to solve this question for this rod, I would call max val of 5, and it would come back and tell me, hey, you can get $15 or 17 or whatever the answer is. Okay, and this is similar to the knapsack. So we can define this as the largest so make these things arrays. And, you know, I listed every possible length. It may be that there's some lengths that we don't want to consider. So I'll just treat this as, you know, data that's not necessarily consecutive. So let's say if we cut off a chunk of rod this length, right? So then that's going to be worth whatever the value of that length rod is. And then the remaining rod that we're going to chop up is the original length diminished by the length of the piece we just cut. And if we decide to start with this 2-inch piece, right, we get the value of that plus the maximum value that we can get by cutting up a rod with the original length diminished by the length of the rod we just cut. The usual caveat, if the length of this piece is longer than the length that we have to cut, we don't do this calculation. So if we're trying to find the maximum value for a piece of rod that's 2 inches in length, right, we can't consider this thing in our pricing table. We can't say, well, we can get $5 plus, you know, whatever we can get out of a -1 length rod that's not physically meaningful. So we would only say, you know, it's $3 plus that or $4 plus that. But this is exactly the same thing as the knapsack problem, right? It's this very recursive, you know, define the value of this function in terms of function calls. And so if we wanted to find max val of 5, what does it look like? Well, so we could cut off a rod of length 1, which would be worth $3, plus max val 4. We could cut off a rod of length 2, which is worth $4, plus max val 3. We could cut off a rod of length 3, which is worth $5, plus max val 2. We could cut off a rod of length 4, which is worth $8, plus max val 1. Or we could cut off a rod of length 5, which is worth $10, plus max val of 0. And so we can trace the execution of this, or the knapsack problem, right, in the form of a n-way tree, right? Now it's not a binary tree, but it's still a tree, but it's got, you know, multiple children for most nodes. And we can, you know, just keep developing this. So max val 3, for example, would be either, you know, 3 plus max val 2, or 4 plus max val 1, or 5 plus max val 0. Five of length 1 for 15 is probably going to be our best bet. So you could write out what this whole tree looks like, right? But you know, we don't do that, right? We just make these calls inside a loop. But this is what happens inside the processor. We effectively visit every node in this very widely branching tree, and as we do this, you know, at each point we record the largest of all of its children. That becomes the value for this. So if we find the largest of these, that'll tell us what maxval 3 is. We add 4, that's the value for this node. And we calculate this, whatever the largest of those is, that's the value for maxval 5. And if this was called from something else, we would return that value and something would add, you know, some price to that maxval 5 and so on and so forth. And this tree in particular is really computationally intense, because to find maxval 4, we're going to need to find maxvals 3, 2, 1, and 0. And to find maxval 3, we're going to need 2, 1, and 0. And to find 2, we're going to need 1, 0. And to find 1, we're going to need 0. Right? And you can start to get a feeling for how deep this recursion is going to be. And it's going to be, you know, in this case, roughly 5 times the depth of the tree. And the branches over here don't go as deep, right? But if we have n things in our cutting table, then each time that we come down a branch, we have to consider, you know, up to n possible branches. And if you look over here, at least, each time that we descend, we calculate maxval for one value smaller. And so this is looking like maybe an n to the n kind of proposition. And knapsack is similar. So if you have 100 items in your inventory, 100 to the 100th, right? That's a big number, right? That's, I believe, a 1 with 200 zeros after it. Yeah. So I think that's Googleplex squared, maybe. So yeah, that's a lot of calculations to do. You really don't want to do that. So we use the idea of dynamic programming, and we say, hey, the first time that I find maxval 3, I'm just going to remember what that is. And then next time that I need maxval 3, I'm just going to read it out of my cache. I'm not going to go through all of the recursion. And that's going to end up looking like something pretty simple. Right, our first call to 5 is going to start off by trying to call 4, which we'll try to call 3, 2, 1, 0. Once we return from here, this will want to use maxval of well, this will get its answer. This will want to calculate maxval of 1, which it will get from cache. And it'll also want to do a recursive call with maxval 0, which it will read from cache. So it's not going to have to actually do any recursion. And this one similarly will need, in addition to maxval 2, it'll need maxval of 1 and maxval of 0, but those will come out of cache. And so we really end up only calling maxval n times. And this goes down to something much more tractable, like an order n squared maybe, which is a lot better than n to the n. All right, so that's another example of this dynamic behavior. All right, well, let's pivot and talk about tries right now, since they're on the quiz. And we're talking about n-way trees anyway for looking at this recursion. And tries are a great example of an n-way tree. So a try is a way to store information in a tree-like structure that makes it very efficient to search for and retrieve data from your structure. Deletion is a different matter. Tries will border on something like order 1. They're extremely efficient. And let's talk about this for storing words. Let's just think about words with uppercase letters A through Z. And let's think about storing these in a tree-like structure. So the idea is, instead of having a node with 2 children, we're going to create a node with 26 children. And we're going to call these children A, B, C, D, all the way up through Z. And all of these are going to be initially null. So if the A child is null, there's no child underneath that node. So initialize everything to null. And don't worry about this little box yet. We'll talk about it in a minute. All right, so here's our initial try, and it's basically empty. There's nothing pointing to anything here. Okay, suppose I want to store the word cat inside my try. Here's what I'm going to do. I'm going to take the first letter of this, which is a C. I'm going to go to the third node in this, the third pointer in this node, which is a C. And that's pointing to null right now. So I'm going to create a new node. And I'm going to have the C point to that. And then I'm going to take the second letter, which is an A, and I'm going to take the A pointer from here, and I'm going to point to another node. And then this third node, since the third letter is T, I'm going to take the T pointer and have that point to another node. And this last field is going to be our end of word field. And just as all of these pointers are going to start off null, end of word is going to start off at zeros. But when I reach the end of a word, when that T points down to another node, I'm going to set that field equal to a 1. So that's just a flag. All right. So this is a node containing a flag, an integer called end of word, and 26 pointers. And each of those pointers either points to null or points to another node. And if it points to a node in that node, then we've got 26 pointers and an end of word, or an end of worry. All right, the word cat is now stored in this structure. How do I know? Because if I look at the C pointer, it's not null, it's pointing somewhere. If I look at where it's pointing, I see that the A pointer in this node is pointing somewhere. And if I follow that, I see that the T pointer in this word is pointing somewhere. And if I follow that, I see that my end of word flag is set. That tells me the word cat is stored in here. So now let's store the word cab. So I'll start with the C, and it's already pointing somewhere. So I'll go down to where it points. And now I'll move to the A. And the A pointer is not null, so I'll go to where that points, and I'll move to the B. The B pointer is null. So to store that letter B, I'm going to make a new node. I'm going to have B point to it. And I'm going to set the end of word flag. If I want to store the word cats, I'll look at the C, it's already pointing somewhere, I'll come down here. The A is pointing somewhere, I'll come down here. The T is pointing somewhere, I'll come down here. My fourth letter is S, so I'll have the S point to a new node. and I'll set the end of word flag to a 1. Now, is the word car contained in this try? Well, let's start with a C. That's pointing somewhere. Let's follow that and look for an A. That's pointing somewhere. Let's follow that and look for an R. And the R is pointing to null. That tells me this is not contained in my try. So if I start following the pointers associated with the letters of a word, and I get to a point where that letter is pointing to null, I can stop right there. I know the word's not contained in my try. And if we look for the word CA, like California, I'll start with a C. That's pointing somewhere. I'll follow that down to another node. I'll look for an A, and that's pointing somewhere. I'll come down there, and that's the end of my word, so I'll check the end of word pointer. The end of word pointer is a 0, so that's not stored in my try. But if I wanted to store the word CA, what do? Start with a C. It's already pointing to a node, so I'll follow that. Move on to the A. That's already pointing to a node, so I'll follow that. That's the end of the word. I'll just change the end of word pointer to be a 1. Now CA is stored in my try. Okay, that's the essence of tries. They're really fun to code because you get to make, a for loop where you malloc memory, which is always like a good day. And you wouldn't actually call your pointers A, B, C, D, E. You'd make an array of pointers, an array of 26 pointers if we were doing uppercase letters. And we would index each letter to an index from 0 through 25 and use that to pull out the right pointer and see if it's null or pointing to another node. There's no need for recursion in any of this. It's a purely iterative operation because we're just starting with the first letter of the word and moving through to the end. Nice. And it's very efficient. The number of operations you have to do to find a word or to store a word is roughly the number of letters in the word. And that's a bounded number. We don't find words that have, 100 letters in them, or 1,000 letters, or 1,000,000 letters. If we're sticking with, say, the English language, your words are mostly, 12 characters or less. There's a few outliers, supercalifragilistic. But, most of your words are pretty small, right? 8, 10 letters might be an average. That's a small fixed number of operations you have to do to look for something inside your structure. And of course, we can also add extra stuff here to store some piece of information that we want to associate with that data. So if we don't just want to know, is this word contained in here or not, but maybe we want to store that word's pronunciation or its definition or its binary encoding to a learning machine, right? We could put that in the same structure. So what's the downside to this? There is no try. Why don't we use this for everything? Large data. So aside from the fact that these nodes are pretty huge, 26 pointers, 8 bytes per pointer, well, that's a chunk of memory, plus a flag. But the way this tree branches out, right, it's a 26-way tree. If it was completely full at a height of 5, it would have, 26 to the 5th nodes in it. It grows really quickly. And it's usually not very close to full, right? We don't find, we'll probably find words that start with every letter, and maybe, most of the branches here will be filled in. But, even if we put in like the entire English dictionary, there's a lot of nodes here that are going to be pointing to null. And the further down you go, the fewer words you find that start with, you know, that particular prefix. But it does take a lot of memory, and so it's a space-time trade-off, the classic. All right, I'll take a look at the quiz. I think that might be enough for you to do the quiz questions, though. But I'll double check that, and we'll talk more about this if we need to, or if you have any questions. All right, we'll be dropping eggs off buildings tomorrow to wrap up dynamic programming. Have a good one. I will see you next time.